And you can see the PPT. Okay, please start recording. Okay, I hope everybody is doing fine. Today would be the last part of our lecture on data link layer, in which we will take about LAN addressing, ARP, Ethernet switches, and VLANs. Okay, I'll stop the video here so that I can reserve bandwidth. Okay, the first thing is about the MAC address. Before the MAC address, we understand that multiple access protocols that we studied in our previous class are extensively used in LANs, that's local area networks. We know LANs are geographically, a network which is geographically concentrated in a specific area. There are, link layer protocols which become part of multiple access protocol. And there are two classes of LANs that are popular. The first one is known as Ethernet LAN, and the second one is known as token ring LAN. There are two technologies of LANs that we come across. Ethernet LAN is also known as 802.3 LANs. It is random access based, and it is one of the most common LAN technologies that is used. They say 1/3 of the world's LANs are based on Ethernet LAN. And the token ring is 802.5. This is basically IEEE originating of it. It's IEEE 802.5. And likewise we have here IEEE 802.3. Okay. Now these are the two types of LAN that we come across. Let's first go to the Ethernet LAN. Now, before I mention this addressing, each node has its identity over the network. And what is this identity? Like at certain places you say IP address. At certain place you say, let's check the MAC address, like you did in the lab, ARP to find the MAC address of it, an equivalent IP address of it. So to understand this, I'll write here about addressing. So regarding addressing, we have, if you're talking about application layer addressing is known as host names. Like you pinged the PC's name. If your PC had the name of, let's say, Ramadan, you pinged Ramadan, you could get the reply of it. So that is the application layer name of it, which we call as host name. Then another addressing that we have is network layer address. This is known as IP address, which is very common, you ping the IP address and so on. And there is another address which is at data link layer, and this is known as MAC address. So we are discussing this time addressing at the MAC, this data link layer. But another thing here is that a question can arise, why we have so many addressing, why not just one? I'll come to this, why we have MAC address and why we have this data link layer. That's an interesting answer for it. But first, let us understand what it is. I'll come to that, why we have MAC address as well as IP. So, this LAN address that we are talking about, or MAC address that we are talking about, this is based on, clear the annotations, this is based on a nodes adapter. LAN address is stored on a nodes adapter. You call it as MAC address, you call it as LAN address, you call it as physical address, you call it as Ethernet address. All are the name for the data link layer's address. And where is it stored? It is stored in the adapter. What is the adapter? The network interface card that we discussed in the previous classes. It's kept in there. And how does it look like? It looks like, here is the example of this LAN address. This one. So what it is basically, a LAN address, also called as physical address, Ethernet address, or MAC address. So MAC is media access control address. And it's of 6 bytes, right? Keep that in mind, that LAN address is 6 bytes. It's written here 48-bit MAC address. So since it's 48-bit MAC address, so we have 2 to the power of 48 possible LAN addresses. It is written in a hexadecimal form. That is an example that has been given here. And how do we get it? When you purchase a network interface card, it's already built in it, so its permanent adapter LAN address is permanent address. The manufacturer of these adapters, they buy a number, they get the MAC addresses in a chunk, from where IEEE manages these physical address spaces. So when the company manufactures it, it purchases chunk of these addresses. That's why no two LANs have the same MAC addresses. And how it is defined, 1A, 2F, BB, and this, it's a flat addressing. There is no hierarchical structure. What I mean by hierarchical structure, like IP address. IP address is hierarchical, in which we have a network part and a host part. In this case, it's just like that. Any notation which is, purchase, which has been given to the company, it's flat. For example, this LAN address is in the adapter. When adapter receives a frame, what does it do? It creates, the data link layer does its functions and puts the work, whatever it has done, in the header. And one thing it also keeps there is attaches the destination LAN address and sends it across. How it gets the destination LAN address, I'll come to that in a little while. It sends across the link, it's a broadcast link, so everybody receives this frame. But only the receiver whom this frame was to be sent to passes this datagram up. It checks that, okay, it matches that this is the destination, okay, this is supposed to be received by me. It takes it and receives. Different, so they discard the frame. But at times, some adapters want to send a frame to all. In that case, what happens? A LAN broadcast address is used. And what is a LAN broadcast address? You put the broadcast address in the destination field of the frame. It's a 6-byte address again, and it is FF, FF, FF. Which means, in this case, means 48 consecutive ones, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, all 48 bits. If this is the case, if the sender sends a frame with a broadcast LAN address, then all the nodes which are within the LAN would receive it. They check the address, and if it's a broadcast address, they accept this address, this frame. Now coming to two parts. Before ARP, why do we need to have LAN address as well as the IP address, which I just now mentioned? So it's keeping layers independent. An important question here. I want everybody to understand that. There are several addressing. We are discussing data layers address, that is the LAN address. There is IP address as well. Now, what are the reasons that we have two addressing? Why not just one? Okay, fine. The first thing is that, LAN address is permanent. So, what happens? If you do not use LAN address, you use IP address, then IP address is to be stored in the RAM of the adapter. Fine. But the problem is that IP address is related to the network that you are connected to. So every time you leave the network and join another network, like you were in hostel, now you came to the lab, your IP address got changed. So every time you move from the network, your adapter would need to get reconfigured or powered up once again. This is a problem. Another thing is that, some layers, network layer protocols are not just about IP and internet. There is IPX, there is other protocols as well. What LAN address helps here is that it acts as a neutral address, wherein if you have a higher layer protocol as IP address, higher layer protocol as DECnet, higher layer as protocol as IPX, it can easily support any arbitrary network layer protocol. So LANs are designed to support any network layer protocol, not just IP and internet. Now you can say, let me make it as a second point, as designed for network layer protocol, not just IP and internet. Okay. So in this case, now the other option here is to use LAN address not to use this LAN addressing adapter. You can ask the same question that, okay, if we have problem that IP address is to be put here and this, not to use this LAN addressing adapter, then what happens here? You see, one thing that you have to note here is when a frame is broadcasted on the broadcast link, we have all the, let's say here, when the frame is broadcasted from this node to all others here, if it's intended, if you have in this as source and this as destination, the packet sent from the source to destination is received by this as well as this. Fine. Now, once you say that node, this network interface card here, that is this one, that is the first thing that you see, is not having the LAN address, we directly take it inside the node. Then what happens is, all the packets that are sent by S to D, okay, millions and millions of packets, they are sent to this as well as this, but they are not intended to be received by this and not intended to be received by this. But if you do not keep a check at the data link layer, at the network interface card, all the packets are to be received by the node itself. They go inside the node. Then what happens there? So what is the problem with this? The problem is that the node would be interrupted by every frame sent on the LAN, even those frames which are not destined to them. So it is necessary that you check it here itself rather than sending. It's like, I give an example. Let's say there is a JEE means exam at NIT. Okay, there are a lot of students that are coming there to give the exam, and there is a center, in lecture halls, there is one of the halls which has been kept as a help center to help students move here and there. Now there are two possibilities there. One is that when the student arrives at the gate itself, you check the student's ID, this roll number slip, and see whether his center is within NIT Srinagar or not. If his center is there, then let him in. If it's not, then don't let him in. Another condition is, okay, don't check at the gate. Let everybody come in. Let the help center decide whether they are to be, whether they have the center within NIT or not. Likewise here, if we do not do the checking of the frame at the gate, okay, all the frames would enter up to the help center and they would waste the time within the halls. So it's better that those frames which are not intended inside the node, discarded at the first entry itself. That's why we have LAN address as well, important, so that each adapter does not pass this frame up to the higher layers, up to higher layer protocol. That is, do not send it inside the parent node. Is this part clear? I hope you understand this part. Why we have LAN addressing as well as the MAC addressing. Any questions? Let's then go to the next part, that is what we call as Address Resolution Protocol, or ARP. You did a command also in the networks lab regarding ARPs. So ARP, basically what is it? Now we know that we need the network address as well as we need the uh, LAN address. We need to have a translation between IP address and the LAN address. Basically, a translation between a network layer address and a link layer address. So who does it? ARP does it, which is Address Resolution Protocol. And how does ARP do? How does ARP does it? ARP does it with the help of ARP module. Now, how does ARP module work here? That's Address Resolution Protocol. Let's consider this as our LAN. Okay. Here. So first we understand here in our LAN here, each adapter or NIC has its own MAC address, and this MAC address is a unique address. Fine. Now, how does address resolution protocol work? When I said when a frame is to be sent from the source to the destination, the source puts the destination MAC address within the frame. So the question is how to determine interface's MAC address knowing its IP address. You have here now you have here a source here, you have destination here. Each node, whether it's source, destination, or other two nodes, each node has its IP address and MAC address. I want everybody here to understand this part. Now, 137.196.7.23, this is the source, wants to send to D, whose IP address is 137.196.7.14. Sending this S, it has a packet created. Fine. It has mentioned within it that this is my destination IP address. So 137.196.7.14. And then it adds one more thing, that is the destination MAC address. That is 5823D7 FA20B0. So both are the destination's address that we have here. One is the destination's IP address, another is the destination's MAC address. But the question here arises that how does the destination know the MAC address here? Okay, IP address, in order to send the packet, you should know. How you get it? For example, you go to google.com, DNS helps you to get the destination IP. So somehow, or you want to send something to your friend, you will first ask him what is your IP address, and you will get the IP address. But how does it get the equivalent, this address, the one which I put for the destination? This is done by ARP module. What does ARP module do? You give the IP address to ARP module, new destination IP address to ARP module. And then what happens here? If you give ARP module the IP address of the destination, ARP responds with corresponding LAN address. Good. So this is how you got it. But at the first place, this is what basically ARP resolves. You give the IP address, it gives you equivalent, or it's the destination's MAC address. Fine. If you go to network layer, you know what DNS is. You give DNS google.com. What does DNS take you to? The IP address of the server of the google.com. So similarly, similar to what DNS does, that's the domain name. Similarly here ARP does is, you give the IP address, you get the equivalent LAN address of the destination. So DNS resolves host names to host wherever they are in the net. ARP resolves IP address for nodes within the same LAN. It's important to understand here that ARP works within the same LAN. The question here arises, fine, ARP gave you the destination MAC address, but how did ARP get this destination address? The ARP got this destination address with the help of ARP module. And what was ARP module having? ARP module had ARP table. And what is this ARP table? It has mapping of IP address to LAN address. And how does it look like? It looks like this. So this is how ARP table looks like. At the top we have IP address. Next we have the LAN address, and next we have the TTL, where TTL stands for time to live. If our IP address here is 137.196.723, Ramanan, keep track of attendance as well. 137.196. Okay, thank you. Just do once, that's it. One 137.196.7.23. What is the equivalent LAN address that I'll get from is 7165F? And so on, time to live, let's say. And likewise, IP address here 137.196.7.14. Its MAC address here 5823D7. Okay. So this is how ARP table looks like. Where is this ARP table? It is in the sender's network interface card or adapter. So all the adapters that are within these LANs would have their own ARP table. And what is within this ARP table? IP address, equivalent LAN address, and time to live. What is time to live? After this time to live is finished, you need to refresh the entry. Entry is not valid for unlimited time, it's valid for a specific amount of time. Oh, so in other words, TTL would indicate the time when the entry is to be deleted from the ARP table. Typical TTL is of 20 minutes. So if now the sender here that we had 137.196.7.23 had to send to the destination 7.14, from this table it checked that this is the IP address where I am sending, its LAN address is this, take this LAN address and put it in the frame. So it's easy that you get the details from the NIC. NIC is where the data link layer actually resides. Okay. Another question now arises, fine, from the ARP table you got it, but how was this ARP table made itself? How did ARP table get to know the LAN addresses? Right? So what happens here, let's try to now understand the second part of it is, how is ARP table actually constructed? So what happens is, when let's say, so when this node was powered up or it joined the LAN, okay, its ARP table also started. What did it do to get the entries of all other devices or nodes which are in the LAN? These three. This sent, this node made a small packet. This packet is known as ARP packet. And what was the sending and receiving destination of it? It sent this ARP packet with sending address as its own IP address and MAC address. And what was the destination address? The destination address was a broadcast address. I just now mentioned a little while ago what a broadcast address is. FF, that is 11111111. Likewise, we have a IP address which is broadcast IP address. So both of them were kept as broadcast. And this packet was broadcasted across the LAN. All the nodes that are within the LAN received it. They checked the destination MAC address, and if the destination MAC address matches their own MAC address, they would accept it. If it doesn't match, they would discard it. But in this case, since it's a broadcast destination address, they would all accept it because they would know that this is information for all. They would check the contents and they would see that it's an ARP query. So you are querying what your MAC address is, and the reply from each of the node, that is here, here as well as here, would be their own IP address as well as their MAC address. So you sent a broadcast frame with an ARP query. The response that all the nodes within the LAN sent is a standard frame, as a normal frame sent, is an ARP message which gave its own IP address as well as the MAC address. They were sent back to the source here, that was the one which sent it. The source receives it back and accordingly puts these entries into this table which is mentioned here, which is the ARP table. And the ARP table gets populated again. So this is how ARP table is built. Now, if you powered up and then after a while some other node joined in, you did not have the entry of ARP of that node's ARP there. So what you do is, so this is like, for example, a new entry came here. This is a new node here that got connected to it. So in that case, what you do is, you do not have the entry of this within this ARP table. You, before actually you could send it to that one, you need to send a message to the node asking for its MAC address. It replies back, you put in the entry here, and then you construct the packet, and then you send the transmission. Keep in mind the ARP is plug and play. You just plug it in and it starts working. ARP is built upon, this is built automatically. And if you power it down, your CPU switches off. All the entries within the ARP are eventually deleted. This is how you can send the data within a LAN using the MAC address. The sending of a datagram from a node within the LAN with the help of ARP works like this. Any questions till now? I hope you understand this part. This is an important part to understand how ARP works. Any questions? Okay, then this is fine. This is within the same LAN. But now the question here is, this is how, okay, this is what I explained just now. How do you query it? You get back and you edit it. But this is sending within the same LAN. This was the figure that we used. All of them have, see the, how do we know that they are the same LANs? See the IP address, this part. See this part. See this part. All of them have a specific part, that is 137.196.7, that is same. This part is known as the network part of IP address. This means that all 4 nodes are within the same network or same LAN. Now how about you are sending from your hostel to your friend within the lab, that is sending to another LAN. How would ARP work here? So this is the second part of this, that is sending a datagram to a node of the LAN. This would represent one LAN connected to a router. Then this would represent another LAN connected to the router here. So when a node on the LAN wants to send a datagram to a node beyond the LAN, that is another IP network, how would we know now this is different? Check the IP address here. Check the IP address here. So A wants to send data to B through R. Now you are sending to your friend here and you know the friend's IP address. Okay. Now to send from A to B, A necessarily has to send through first hop router or gateway which is connected to it, which in this case is R here, router. And you can see that this node has IP address network part, and this NIC of router has this IP address network part as same, which means that this is one LAN. Okay. So what does ARP do here? A is powered up, it boots and it makes an ARP table. In the ARP table, there will be entries of this node as well as the network interface card of router R. Router also has IP addresses as well as MAC addresses, but router has many interfaces, so each interface or each network interface card has its own IP address as well as its own unique MAC address. Now when the node A made its routing table, ARP table which looks like this, it makes an entry of this as well, that is R. It makes the entry of R. So now you had a table ARP with R. Now the packet that is to be sent would have the source address which is mentioned here. Source address of what? This A, that is 7429. What is the destination address it would put? The ARP works within the LAN itself. It doesn't work beyond the LAN. You do not have the MAC addresses of all the PCs that are within NIT or beyond NIT. No, within that LAN you can have the MAC addresses. But you have the MAC addresses of the gateway through which all of your traffic you are connected to would go here. So in that case, the destination would be to the gateway's MAC address, that is this one. It would put its own source address like given here, IP address, but the destination IP address is not that of the R, that is 1111. The destination address is of B, that is 222222, that is put in the packet, and the packet is made and it is sent across the network. Now what happens here? This packet is broadcasted, it is received by this, it is received by this as well, because they are within the same LAN. LAN does broadcasting. When the packet checks here the destination MAC address, it sees that it's E69. So what does it do? It discards it, says no, this is not my packet. When our router checks the MAC address, it sees yes, it is E69, E9, this is intended to me, moves on to the IP address and checks that the destination IP address is 22222222, which is not its address, but its router. It has its own routing table which works in network layer. It knows now that this is to be passed on to this link. Once this is passed on this link here, at this point we have outgoing link here. Outgoing link has its own network interface card. What does it do here? It uses the ARP table of this network interface card which is mentioned here, this one, and changes the destination MAC address here from this to 49BD that is given here, puts this within the packet here and then broadcasts it. This one receives it, this one receives it. How did it get the destination here? Because it is within this specific LAN. Using ARP, it had the MAC address of B as well as the other one. So now we know that packet is broadcasted here. This one received it, this one received it. This one checked the destination MAC address. Its own is 88, but the one which was intended is now not this one. Then it was 49BD in this, so it discards it. Instead, when this one B receives this packet, it sees the destination MAC address is matched, then goes to the IP address is matched, it accepts the frame. That that is how a packet is sent from the datagram, when the packet is sent across the LAN. Is this clear? Ramanand? Is this clear? Kind of, sort of. How about others? I have here Abhinandu, Moli. Najm Saqib, Mehreen, Isma, Asha, Abhishek, Subhash, Varun Pandey, Vikas Kumar, Sandesh. All clear? Everybody understood? In this case, we can have Ethernet as a bus, we can have Ethernet as a ring. This would make clear to you that Ethernet can be one of the two. What happened to Ramanand? You're there? Okay. Namaste. Alright, so this slide would explain to you that Ethernet can be any of the topologies, any of the physical layer topologies. Now, how does Ethernet frame look like? This is the frame that we see when data link layer works on it. To begin with, the first thing that I will take here is the payload. This is what you got from network layer, data or payload. What is inside it? How is it? We are not concerned with it. It's the payload that is to be delivered. And what do you have before and after it? It is what the data link layer does the work by adding the header and the trailer. Both together we call it as header. So the sending node encapsulates the IP datagram, that is the payload here, within the Ethernet frame, that is the other things that we have added to it, and then passes the whole of it to physical layer, and physical layer receives this at ones and zeros. And what is the Ethernet frame structure? They are having 6 fields. One field is the actual payload, which is given here. This we call as the data field. I just type CSS. Okay, what is the data field here? It can range from 46 to 1500 bytes. And what it does basically, it carries the IP datagram. This 46 is minimum and maximum is 1500 bytes, the data that we have. And why do we have this 1500? This we know as, this 1500 is known as MTU. What is MTU? Maximum transfer unit. This is the maximum transfer unit, all right? Now it's like, you have a truckload of, let's say, 1,500 bricks that you want to carry, and the truck capacity is 1,000 only. In this case, let's say here 1,500, we have a truckload of 2,000 bricks, but the maximum bricks that a truck can carry is 1,500 only. So if your data comes as 2,000 bricks, you would have to first carry 1,500 bricks, and then another truck would carry 500 bricks that is remaining on. Which in other words means that if the network layer gives a datagram which is of the size more than 1,500, the sender's data link layer has to fragment the data, that is break up the data, like I said, 2,000 into 1,500. But normally they do, the network layer would not do that. They would try to have the data sent to the data link layer the maximum possible as MTU, the maximum transfer unit. It will not try to go beyond that, so that there is no fragmentation of data done by the data link layer. And how much is the maximum that data link layer would carry? 1,500 bytes, which we call as MTU. And minimum is 46. The next part is the destination address that we see here. What is this destination address? This is the destination MAC address. And how did we get the destination MAC address? This is what we understood just now by ARP. This is of 6 bytes. Likewise, source address. This is the source MAC address, again of 6 bytes. ARP gives these details and are put within it. Then there is a field which is known as type field. And what does type field do here? Here in between you can see there is small type field. It's of 2 bytes. It basically multiplexes the network layer protocol. We just now discussed in the beginning of the class that why we need IP address, why we need the network address as well, this LAN address as well. We said one of the reasons is keeping the layers independent. Then we said that MAC address can be providing or receiving data from any arbitrary network layer protocol. So any arbitrary network layer protocol here means that there can be different types of application that come across here. The receiver should know to which layer protocol it is passing. It demultiplexes the contents of that data field. This is where type helps it. Okay, like ARP gives its own type number to understand this. So it's also mentioned, you can see here, that type indicates higher layer protocol, mostly IP, but other possible as well, normal IPX, AppleTalk, and so on. So if you mention IP there within the type, within that 2 bytes, it gets to know that the data that I am passing on to is to be passed on to IP. If it's IPX, it will be IPX, and so on. Then we have CRC. Okay. This we discussed. You saw the video of CRC, cyclic redundancy check, how it works. Cyclic redundancy check is of 4 bytes. It detects if there is any error introduced within the transmission. If yes, there is an error, it discards it. If not, then it passes on to the higher layer protocol. Before this, there is another one that we call as preamble, which is of 8 bytes. The Ethernet begins with a preamble. This is the start of it. Okay, why I'm mentioning here again is the start of it, because this would be used in my topic. This is the start, means this is the front of it. So Ethernet begins with a preamble, and what is preamble? Preamble is of 8 bytes. We have 8 bytes here, we have 6 here, we have 6 here, we have 2 bytes data depending upon how much you are sending, and after this we have CRC as 4 bytes. Now, the value of the preamble here is given here. The preamble, the first 7 bytes have the value of 10101010. The last byte has the value of 10101011. The last one is 11. Now the first 7 bytes serve as a wake-up call to the receiving adapter, and it is used to synchronize the receiver's clock with the sender's clock. The last 2 bits of the 8th byte of the preamble, that is consecutive 11 here, alerts the receiver that the next 6 bytes which are coming after this, that is this one, this is the last one, is the destination address. So after this 11, after waking it up with these, ending with 11, whatever is coming after this, it is the 6 byte destination address. So it's like a start call, start of the frame. This is what the start is. So you say the destination would get to know about the start of it once it starts receiving it, and then it notes that this is the wake-up call. After wake-up call 11, now I'm expected to receive the destination address. How would the destination get to know that this is the end of it? Here, you don't need any signal, any pattern to denote that this is the end of the frame. Why? Because simply the absence of current within the channel would detect that frame has ended. That's why we don't have any ends there denoting that. Ethernet, few points that we need to take from here is connectionless. Okay, it's unreliable, doesn't send any acknowledgement back, and so on. It uses unslotted CSMA CD with binary backoff. There are different standards of Ethernet. You hear about 10 base X, 10 base T, 100 base X, 100 base T, where the 100 here denotes this one. The 100 here, this 100 denotes that speed of it, 100 Mbps. Then we have, FX, TX, VX, and so on. They denote the technology that you are using, whether you're using coaxial cable, whether it's a bus technology, whether they are T connectors, and so on. This is denoted by the last 2 letters that are used there, SX, BX, TX, FX, and so on. Typically these 100 base TX, 100 base T, they are called as fast Ethernet. They are 100 Mbps and above Ethernet technologies. Can use standard twisted pair for transmission. Nowadays we have gigabit Ethernet as well. They can, send at much faster rates. Here you can see the blue ones, TX, T4, T2 indicate that they are of 100 Mbps speed and they are copper twisted pair physical layer channels. The red one here where it denotes about FX, SX and BX are of fiber physical layer. Okay. This ends this part of it. And the last part that we'll come across is about Ethernet switch. The one thing I want to mention here, one thing is hub, the second thing is switch. This would be the last part of today's lecture. Few devices that we come across in networking are hubs, switches, bridges, and so on. Let's first take hubs. What are hubs? They are simply simplest way to connect. They simply broadcast the bit on all the interfaces that it receives. So hub cannot break a LAN into multiple domains. They have a single collision domain. So if you use hub for, let's say, 5 departments, all are connected within the same LAN. And what is the problem if you're connecting within the same LAN? Obviously, it's a broadcast LAN, so all the packets across all the departments would be received by everybody if it's a common LAN. So we call this as one collision domain. Also, if different departments have different Ethernet technology, it will not be able to connect them together. Okay? They do not buffer frames. They are very simple devices as such. There should be maximum allowable number of nodes within a collision domain. There should be a maximum distance between those. There should be maximum, layers within these. So hubs are more or less now outdated. We do not see hubs nowadays typically in networking domain. The second one that you might have heard about is bridges. Bridges operate on Ethernet frames. Okay. They are layer 2 devices. That is the data link layer. They are actually fully fledged packet switches that forward and filter frames using MAC address. Now once they forward and filter frames, this means that when a frame comes to a bridge or a bridge interface, bridge does not copy the frame on all the other interfaces. Instead, it checks the layer 2 destination address and then sends it to that specific address as well. So we have isolated collision domains here, and it can interconnect different LAN technologies. No limit of how big a LAN is to be. So I came here to 2 points. One is filtering, another point is forwarding. Since bridge is a layer 2 device here, data link layer device, we need to understand what we mean by filtering, what we mean by forwarding. Filtering is the ability of a bridge to determine whether a frame should be forwarded to some interface or it should be dropped. This is filtering. Ability of a bridge to determine whether a frame should be forwarded to some interface or it should be dropped. And what is forwarding? This is the ability to determine the interface to which the frame should be directed. Forwarding is actually ability to determine the interface to which the frame should be directed, then not just the ability, then directing the frame to that interface. How do they do it? Bridges have their own table, which is known as bridging table. Like we saw ARP table, here we have bridging table which has LAN address of the node, bridging address as well as TTL. Bridges are again, autonomous. They are self-learning. They are plug and play. Okay, Ramanand, I think I'll stop here now. I'll continue with this in the next lecture. Do you have any questions till now? A little bit about switching that I will mention in our next class, and then that should be the end of this one. All right. Okay then. Okay, everybody take care. I'll see you in the next class then.